all know that a 3 by 3, a typical 3 by 3 matrix has 3 eigenvectors up to scaling, of course, over the complex numbers. So typical 3 by 3 matrix will have 3 eigenvectors. So today I'd like to ask the question, how many eigenvectors does a 3 by 3 by 3 matrix or 3 by 3 by 3 tensor have? And then towards the end, time permitting, we'll talk about singular vectors as well. And we're going to ask the analogous question for singular vector triples. So let's get started. Everything I say in this talk is in this article called Tensors and the Eigenvectors that appeared last summer in the notices of the AMS. These are the pictures that go with the article. They represent sort of a picture of the spectral theory of tensors, and I'll explain what these pictures are towards the end of the talk. So for me, a tensor is simply an array of numbers. So a d-dimensional array of real numbers or complex numbers indexed or indices I1 up to ID. Now if d is 1, we call this a vector. If d is 2, we call this a matrix, and so on. So a tensor of format n1 by n2 by nd has product many entries, n1 times n2 up to nd. Now the simplest vectors are rank 1 vectors. So rank 1 vector is simply an outer product matrix. A tensor is simply an outer product of vectors. So you all know that a rank 1 matrix looks like this, right? It's a row vector times a column vector, and a rank 1 tensor looks like this. Okay, so same idea. The set of all tensors of rank 1 is an algebraic variety defined by quadratic equations in the tensor entry called the Segre variety. And I will jump back and forth in this talk between the real numbers and the complex numbers. We already did that when we talked about the 3 by 3 matrix, because it could happen that a real matrix has complex eigenvalues. Now a tensor has rank r if it's the sum of r tensors of rank 1, not fewer. So this is the same definition. One of many equivalent definitions for the rank of a matrix is the rank of a matrix is the smallest number of rank 1 matrices you need to decompose your matrix in. It's the same definition for tensors. And in tensor decomposition, we're interested in, given a tensor, to decompose it as a sum of rank 1 tensors using as few summands as possible. So this is a fundamental problem that comes up in many, many applications in engineering, statistics. In statistics, these things are called contingency tables. Nowadays, many large data sets come in the form of tensors rather than matrices, and tensor decomposition is a very basic question. Here's a textbook reference on the geometry of tensors. There's the book by Landsberg that I can highly recommend to the graduate students in the audience. Now, Mike Mahoney told me this morning that really all matrices are symmetric matrices, right? Why should we care about any matrices that are not symmetric? Well, let's extend this philosophy to tensors. So a tensor that is symmetric is an n by n by n by n tensor whose entries are unchanged under permuting the indices. So a matrix is symmetric if the ij entry is equal to the ji entry, while a 3-dimensional tensor like my Rubik's Cube is symmetric if the ijk entry is equal to the ikj entry is equal to the jki entry, and so on. Right? So that's a symmetric tensor. Now, this is the degrees of freedom. So the space of symmetric tensors, d-dimensional tensors of format n by n by n, has this many distinct entries, n plus d minus 1 choose d. That's what you learn in your freshman discrete math class when you count with bars and stars. Now a symmetric tensor has rank 1 in the symmetric sense if it's the outer product of the same vector with itself many, many times. Right? So a symmetric matrix is a matrix that's a row vector times a column vector, and they're the same vector. Right? That's a symmetric matrix. And a symmetric tensor has rank 1 if it's the sum of r such tensors. Now this brings us to the first open problem. There are 2 open problems in this lecture, and the first open problem is Comon's conjecture. So this is Pierre Comon, an engineer from INRIA working in signal processing, and he asked whether the rank of every symmetric tensor is equal to its rank as a general tensor. It's an open problem. So the answer is true. The answer is yes for matrices. So let's go over the statement of the proof for matrices. Suppose you have a symmetric matrix and it has some rank. That means you can take that symmetric matrix and decompose it as a sum of rank 1 matrices, a small number of them. But those rank 1 summands may not be symmetric, right? You could have a bunch of rank 1 matrices that add up to a symmetric matrix. But it's a miracle. So here's this non-symmetric decomposition. So T is my symmetric matrix. And I've written it as a sum of R non-symmetric rank 1 matrices. However, you know, and you teach to your linear algebra students, that this decomposition can be transformed into another decomposition where the summands are in fact symmetric. Right? So for matrices, if you have a symmetric matrix decomposed into a small number of rank 1 summands, you can arrange for those summands to also be symmetric matrices. It is an open problem whether this is true for tensors. It's known in some special cases, but in general we don't know. And if you get bored by the rest of this lecture, you can try to solve Comon's conjecture. Now let's get to eigenvectors slowly but surely. Now the best way in my view to do this is to identify symmetric tensors with homogeneous polynomials. So if I have a symmetric tensor, I can equivalently write it as a homogeneous polynomial of degree d in n variables, x1, x2 up to xn, where the entries of my tensor are simply the coefficients of the polynomial, and that's a bijection, right? So we have the bars and star binomial many entries in the symmetric tensor, and then these are the corresponding coefficients of this polynomial. Now low rank decomposition for tensors translates into what's called the Waring decomposition of the polynomial. So the tensor, now regarded as a polynomial, has rank r if I can write it as a sum, a linear combination of r d-th powers of linear form. So rank 1 symmetric tensor is a d-th power of a linear form. And if I can decompose it in this fashion, this is just a translation of the definition on the previous slide. Now over the complex numbers, I can subsume this multiplier lambda j into the d-th power, but over the real numbers, maybe I have a signature. So I'm going to retain the lambda j here for convenience. To define eigenvectors, I look at the gradient of my polynomial. So the gradient is the vector of length n, whose coordinates are the partial derivatives. So in the first coordinate, I have the derivative of t with respect to x1, then the derivative of t with respect to x2, and so on. That's the gradient vector. So the gradient vector is a vector whose entries are homogeneous polynomials of degree d minus 1 in the n unknowns. And as such, it defines a map from n space to n space just by plugging in. Right? So I have a vector of length n, each coordinate of which is a polynomial in n variables. By plugging in, I get a map from n space to n space. We say the vector v is an eigenvector of the tensor, or equivalently of the polynomial, if it's fixed under this map up to scaling. So if my vector v gets mapped to lambda times v for some scalar lambda, well, lambda again could be real or complex, and this lambda then I would call a corresponding eigenvalue. Okay, so the eigenvector eigenvalue equation just says that v is fixed up to scaling by the gradient map. So this is my definition of eigenvector. In this talk, thanks Michael for encouraging me, I'm going to stay with symmetric tensors only. There is also a version for non-symmetric tensors. Now what is this good for, and how does this tie in with what you know, say statistics, optimization? So let me first argue that this is really a very, very, very well-known classical optimization problem, namely the problem of maximizing a homogeneous polynomial over the unit sphere in n space. The unit sphere is the set of all points where the squared sum of coordinates is equal to 1. So maximizing a homogeneous polynomial, this is well-defined, has a maximum, it's a compact set. So how do we solve this? Well, it's a constrained optimization problem, so let's write down a Lagrange multiplier formulation. And the Lagrange multiplier equations are exactly the eigenvector eigenvalue equations. Right? So if lambda is the Lagrange multiplier corresponding to this constraint, then the condition is that the gradient of t is equal to gradient of t evaluated at a point is v is lambda v. So fact is the critical points are the eigenvectors of t. Now it's convenient for the rest of our discussion to replace the vector space, the n-dimensional vector space, by the corresponding n-1 dimensional projective space. So in English, I'm just going to identify two vectors if they're the same up to scaling. Okay? Now then I can look at my gradient map also as a map from projective n-1 space to projective n-1 space, because the entries of the gradient vector are homogeneous polynomials of the same degree. This is well defined, right? I get a map from projective n-1 space to projective n-1 space. That's a convenient way of arguing away the eigenvalue, because now eigenvectors are simply fixed points of the gradient map. Right? So by definition, an eigenvector or eigenpoint is a fixed point of the gradient map of the polynomial that has been identified with the tensor. Now this map, here I have a dashed arrow. This means this is a rational map. So there are some poles. It could happen that it's not defined at some poles. Namely, it could happen that you have a non-zero vector at which all the derivatives vanish. Right? So it could be that the hypersurface defined by t equals 0 has some singular points in projective space. And at such a singular point, all the partial derivatives vanish, and it would not be well defined, right? Because the image would be 0. So there's a little bit of fine print expressed by the dashed arrow. This is a rational map, and there might be poles. Now, of course, this is an arbitrary, pretty arbitrary polynomial dynamical system, right? So I have more or less every polynomial self-map of the projective space has this form, and so we have to be very, very careful in this talk that we want to stay away from all the difficulties of dynamics. Right? So if we study dynamical system, very difficult things can happen, like Julia sets and all these kind of things, the fractals. So we want to stay away from the difficulties of dynamical systems. We want to stay on the safe and easy ground of algebraic geometry. Now, the spectral theory of tensors as a field in, let's say, applied math, scientific computing, was pioneered by Lim and Qi. They have a nice article from a couple years ago. But what I'm trying to say here, this is really goes back hundreds of years, right, to the problem of maximizing a polynomial on the sphere, or to finding the fixed points of a polynomial self-map of projective space. Let's get back to what we learned as undergraduates in linear algebra, and let's tie this in with what you're very familiar with in the case d equals 2. So for d equals 2, tensors are called matrices, and we focus on symmetric matrices, and we all know that real symmetric matrices correspond to quadratic forms. So a real symmetric n by n matrix has n plus 1 choose 2 entries, and these are the coefficients of a quadratic form. Now with the real numbers, we have the spectral theorem, which says that our quadratic form can be decomposed, if it has rank r, as a sum of r squares of linear forms. This is our low rank decomposition. But more is true. The lambda j's in this decomposition are the eigenvalues, and the vectors that make up the linear forms are real and orthonormal. That's the content of the spectral theorem. Now, how do you find the eigenvectors? Now, this is extremely embarrassing, doing this in front of Jack, right? Because many of you here know this much better than me, but at the risk of taking Coles to Newcastle, well, how do we find eigenvectors? Well, basically, we iterate the map, right? So the gradient map is now a linear map. It's the linear map associated with the matrix T. Right? If T is a quadratic form, then the gradient vector, the partial derivatives, are linear forms, and the gradient map is simply the linear map of the matrix. And the eigenvectors are the fixed points of this linear map when thought of in projective space. And again, how do we find eigenvectors? Well, many of the algorithms that are used, correct me if I'm wrong, are basically versions of iterating the map. Right? So we're iterating the map with the hope of landing at a desired fixed point, and these are the eigenvalues. Okay, so this you're very familiar with. Let's go one size up. Let's think about the n by n by n Rubik's cube. So let's go over this for an n by n by n symmetric tensor. So they correspond to cubic forms, just as before. Matrices correspond to quadratic forms. Well, the low-rank decomposition we might be interested in are decomposition of the tensor into a sum, a linear combination of third powers of linear forms. And we also might be interested in the eigenvectors. So they are the fixed points of the quadratic gradient map, right? So if t is a cubic polynomial, then the gradient vector has coordinates, the partial derivatives that are quadratic forms. So here we have a quadratic self-map, and the fixed points are the eigenvectors. Now here's what happens. Unlike in the matrix case, the eigenvectors are not the vectors you see, Vj, in the low-rank decomposition. So there are two things that are interesting. There's the spectral theory of matrices that's very interesting, and there's the low-rank decomposition of matrices that's very interesting. And for matrices, they happen to coincide. That's the content of the spectral theorem. But for tensors, they don't, right? So maybe that's bad news. But for me, that's actually not bad news, because the matrices are weird, right? The normal behavior is that these are two separate, interesting things. The spectral theory of tensors is interesting. Low-rank decomposition of tensors is interesting. They just happen to coincide for matrices, and in general, they don't for tensors. Well, not for arbitrary tensors, but there are some tensors where they do coincide. And those tensors we call ODCo. So let me take a couple minutes to talk about that case of ODCo tensors. So ODCo is an acronym. It stands for orthogonally decomposable. And a symmetric tensor is ODCo if it satisfies the conclusion of the spectral theorem. So a tensor is ODCo if I can decompose the associated polynomial as a sum of n dth powers of linear forms, where now I make this to the definition, where now the vectors I see in the decomposition form an orthogonal basis of r to the n. Okay, so I take this as the definition. So a tensor, a symmetric tensor, is ODCo if it satisfies the conclusion of the spectral theorem. Symmetric matrices are always ODCo, that's the spectral theorem, but symmetric tensors in general are not. Now, being ODCo is a pretty serious constraint. Well, in particular, you can see it already says that the rank is at most n. Well, let's think about our Rubik's cube. Let's think about a 3 by 3 by 3 tensor. A random 3 by 3 by 3 tensor has rank 5. Right? To count parameters, a random 3 by 3 by 3 tensor has rank 5. But to be ODCo, its rank is at most 3. That's already a constraint. Beyond that, the summands you see in the decomposition, they should be orthogonal. So that's a very serious constraint. Now, ODCo tensors are very, very nice. So that's been recognized in the machine learning community. So here's a theorem due to Anand Kumar and her collaborators from a couple years ago on learning latent variable models. And it says the following. Suppose in such a decomposition everything is real and the lambdas are positive. Then the Vj that you see in the decomposition are precisely the robust eigenvectors of the tensor, the robust fixed points of our dynamical system. Now, I need to define robust, right? So robust simply means there's a positive probability of reaching that fixed point by iterating the gradient map. So a fixed point, an eigenvector, is robust if there exists a full-dimensional open subset in R to the n, such that starting anywhere in this open set, I'm going to reach the desired eigenvector. So those are the robust eigenvectors. Those I will reach with positive probability if I pick my starting point at random in the gradient iteration. This theme was picked up also in the numerical linear algebra community. There's a nice article by Tammy Calder with this charming title. So symmetric, so ODCo tensors are particularly interesting. Now, why is this so popular in machine learning? So these guys, they have a method. So you take data. So in this situation, this is some cumulant tensor. So you have some symmetric tensor. Now, the given tensor is not ODCo, right? The given data tensor will not be ODCo. But they have a process called whitening that takes your data and replaces it by some ODCo tensor. Okay? Now then you apply this trivial method of finding the robust eigenvectors, the decomposition, and then you unwhiten the output and draw conclusions. And that seems to be work very, very well in this context. Now maybe for linear algebra experts, this theorem is false for matrices. So in this theorem, D is at least 3, right? Because if you have a matrix, there's only one robust eigenvector. There's only the Perron-Frobenius eigenvector you can converge to, right? If you do a random symmetric matrix, you can only run into the distinguished Perron-Frobenius eigenvector. What we're saying here, there's exactly n of them, and you can reach them all. Now, since ODCo tensors are so nice and so special, what can we say about them? Well, they form a very nice algebraic variety of this dimension, n plus 1 choose 2. This was first studied by Robeva, and I'm now going to talk a little bit about a different way to think about ODCo tensors. The next slide is going to be the algebra slide in this talk. So bear with me, this is the most algebraic slide in the whole talk. There's a different way to think about tensors. You can think about a tensor, an n by n by n tensor, for example, as giving you the structure constants in a multiplication, in an algebra structure on R to the n. So I claim giving an n by n by n tensor is the same thing as giving R to the n the structure of an algebra. So let me explain this. So suppose we take R2, n equals 2, and let me call A and B the basis vectors, a choice of basis for R2. Well, suppose I have a 2 by 2 by 2 tensor, right? Then I can define a multiplication by saying A times A is, this scalar times A plus some other scalar B, and so on. BA, AB, BB, right? So I need 8 structure constants to specify how I should multiply the two basis vectors, and then I extend by bilinearity, right? So that defines a structure of multiplication R2. Now, this multiplication is not commutative in general. It's not associative in general. It's just some algebra structure. Let's try this out, right? So if I go B times A, then you get some quadratic thing times A. You can always expand the basis, right? Some other quadratic thing times B. If you do the other bracketing, B times A, you get this thing, right? So it's not associative and certainly not commutative in general. Now maybe things get a little bit better if we take a symmetric tensor. So a symmetric 2 by 2 by 2 tensor has 4 distinct coordinates, because a symmetric 2 by 2 by 2 tensor is a binary cubic, a homogeneous polynomial in 2 unknowns, x and y, of degree 3. Here we go. So let's look at a symmetric tensor. Now for symmetric tensor, things are slightly better because the two black coefficients now coincide, right? So for symmetric tensor, T001 is the same as T100, and this is equal to that. So these two black things are now equal, but the two blue things are still not equal. So still, we don't have associativity. However, and this is the theorem, so this is the theorem to Bora-Levy and her collaborators, is that the ODCo equations say precisely that T defines an associative algebra. So a tensor, a symmetric tensor, is ODCo if and only if the algebra structure is associative. So let's test this. So associative in particular says that this thing is equal to that thing. Well, that says that these two things are equal, and it's exactly this quadratic equation that characterizes ODCo tensors of format 2 by 2 by 2. So there are different ways. It's a little bit surprising that the algebraic condition of a multiplication being associative is equivalent to the conclusion of the spectral theorem holding and having these nice applications. Now I've spoken for 26.5 minutes and I have not yet answered the question. So let's get to the question. How many eigenvectors does a symmetric 3 by 3 by 3 tensor have? Just to be on the same page, this picture equals that picture, right? This is a symmetric 3 by 3 by 3 tensor. It has 10 entries, right? Out of the 27 dots you see, there are 10 distinct entries, and they are the 10 coefficients of a ternary cubic of a homogeneous polynomial of degree 3 in 3 unknowns, and that's the same as an elliptic curve in the plane, right? So this picture of a cubic curve in the projective plane, a cubic curve in the projective plane is the same as this. Okay, so as an optimization problem, how many critical points does a homogeneous cubic have when you maximize it on the unit sphere? Well, the answer is 7. And turns out that the ODCo tensors exhibit the generic behavior. So here's an ODCo tensor written as a polynomial. So if we take the Fermat cubic, x cubed plus y cubed plus z cubed. So as a tensor, this means I fill this with all zeros except the long diagonal, has the 3 1s. Right? So that's the unit tensor, if you wish. Now, why is this ODCo? Well, you look at the corresponding vectors, right? 1, 0, 0, 0, 1, 0, 0, 0, 1, right? They're orthogonal. Right? So that's an ODCo tensor. So another way to say ODCo, it means to be in the orbit of the Fermat polynomial under the orthogonal group. Okay, so let's calculate the eigenvector. So we're supposed to take the gradient map, right? So the partial derivatives of this are 3x squared, 3y squared, 3z squared. Well, we're in projective space, and the characteristic is not 3, so we can divide by 3. So the gradient map is simply the squaring map, right? So the gradient map from P2 to P2 is the map that takes a point with homogeneous coordinate x, y, z, and squares every coordinate. Now that has 7 fixed points. Those are exactly the 7, 0, 1 points that we have. The blue points, so these are the fixed points under this map in projective space, right? So in projective space, 1, 1, 0 is the same as 17, 17, 0, right? So those are the fixed points. Now the first 3 are the robust eigenvectors, and the last 4, the red ones, are not robust. Let's go over the definition of robust again. I pick a random starting point. Okay, like 3, 5, 11. Okay, so I start with, then I apply this map. I apply the gradient iteration. It's going to converge, right? This P2 is compact. I keep squaring. Dividing is, things don't blow up, right? Because I'm in projective space and I'm going to converge to the last one. So I'm always going to converge under the squaring map to the unit vector that indexes the largest coordinate of where I started, right? So if I start, the third coordinate was the largest in my starting point, I'm going to go to this one. Now it could happen with probability 0 that I land on these, but these guys are therefore not robust. So the answer is 7. A 3 by 3 by 3 general tensor has 7 typically complex eigenvectors. Here's the general count. Let me give you the formula. So if we have a d-dimensional tensor of format n by n by n by n, then the number of complex eigenvectors is given by this expression. So d minus 1 to the n minus 1. That's divisible by d minus 2. So divide, and you get this geometric series polynomial. Right? Now let's first make sure that this agrees with what we know for matrices. Right? So for matrices, the case d equals 2. So we plug in d equals 2, then this is 1 plus 1 plus 1 plus 1 is n. Okay? So indeed, a symmetric n by n matrix has n eigenvectors, and this is the formula in general. So we actually wrote a little paper that proved this with Cartwright, who's at Tennessee. So Dustin Cartwright and I wrote a little paper that answered this question that Tammy Calder asked us. Later we learned that this was known in complex dynamics, so this is the formula. Let's do one more example. Let's look at a 3 by 3 by 3 by 3 tensor. Such a symmetric tensor has 15 distinct entries because a 3 by 3 by 3 by 3 tensor corresponds to a ternary quartic which has 15 terms, x to the fourth, x cubed, y, blah, blah, z to the fourth. The number of eigenvectors is 13. If you plug in, here's a way to visualize this four-dimensional tensor. So you take this four-dimensional tensor, it has 81 entries, and then you slice it into three-dimensional tensors, and this is a way to visualize this. Now, of course, this count is for generic tensors. Just like for matrices, there are special matrices, right, where eigenvectors come together and you get eigenspaces and so on. The same will happen for tensors. So let's talk a little bit about this degenerate situation. So there's a very, very big polynomial called the eigendiscriminant in the entries of the tensor, which vanishes when two of these eigenpoints come together. Right? So this is the general count. I have for a random tensor, this is the count, but for special tensors, there's a big polynomial in the entries of this tensor, a discriminant, which will vanish when two of these solutions come together. Here's a theorem. The degree of the eigendiscriminant is, in terms of n and d, it's a homogeneous polynomial of this degree, n times n minus 1 times d minus 1 to the n minus 1. Again, it's always good to check the matrix case. So if d is 2, then this discriminant has degree n times n minus 1, and that is indeed correct, right? So this is the discriminant of the characteristic polynomial of an n by n matrix. If you work that out, the discriminant of the characteristic polynomial of a square matrix is a polynomial of this degree. Now here in this case, for example, in the ternary quartic case, the eigendiscriminant will be a big polynomial in all the entries of degree 54. Now we were very interested in this paper with Abo and Siegel. We were interested in so-called eigenconfigurations. Well, suppose, in this case, let's say you have 13 vectors in three-dimensional space. You ask the question, are these the eigenvectors of some 3 by 3 by 3 by 3 tensor? Right? Now, for matrices, the answer is easy. Right? So if you have any basis of r to the n, it's going to be the eigenvectors of some square matrix. Well, if it wants to be, if you want the matrix to be symmetric, then there's an extra constraint. But other than that, any basis occurs as the eigenvectors. That's very, very false. This is non-trivial. So it's very, very non-trivial to characterize configurations that are eigenconfigurations. And one thing that makes this hard geometrically is that this property is not invariant under projective transformations. It's not invariant under the general linear group. It's only invariant under the orthogonal group. Let me say this again. If you have 13 points in the projective plane, maybe it's an eigenconfiguration. If you apply a projective transformation afterwards, in general, it's not an eigenconfiguration. Very weird for geometers. But the reason is the following. When you teach linear algebra, often you teach the following thing. Here's a vector space, and here is the dual vector space, right? The vectors in the dual vector space are linear functions on the primal vector space. And they are not the same. They are two different vector spaces unless you choose a quadratic form that identifies them. But actually, in our definition of eigenvectors, we tacitly chose such a quadratic form. So if you unravel the definition of eigenvector, it was really a fixed point of the gradient map. But the gradient really lives in the dual vector space. So tacitly, I've chosen a quadratic form, and that means that this eigenconfigurations and the eigendiscriminant is not invariant under the general linear group, but only invariant under the orthogonal group. Now here's another thing that the eigendiscriminator is good for. It carves up tensor space into regions where the number of real solutions is constant. Right? Now here the complex count is 13. There are 13 complex eigenvectors, but you're only interested in your application, you're only interested in the real eigenvectors. Right? If the complex count is 13, then the number of real eigenvectors will be 13 or 11 or 9 or 7 or 5 or 3 or 1. Which is it? What's the average? Right? What's the average number of real solutions? This was answered last year in a beautiful paper by Paul Breiting. So the title of his paper is The Expected Number of Eigenvalues of a Real Gaussian Tensor. So a Gaussian tensor is one where the entries are independently drawn from the standard normal distribution. Right? So random matrix theory is well established. So this is a sort of a study in random tensor theory. So we're picking the entries of the tensor 0, 1 Gaussians independent. And then Paul gives an exact formula for the expected number in terms of hypergeometric integrals. He doesn't quite get the moments, but he gives a beautiful formula for the expected value. Let's look at this histogram. So this is for 3 by 3 by 3 by 3 tensor. So we know the complex count is 13. And this histogram shows the real count. So most of the time, there will be 3 of these will be real, sometimes 1, sometimes 5, rarely 7, occasionally 9, very rarely 11, and really, 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 really rarely 13. Okay? So that's the real distribution of the eigenvectors of such a 3 by 3 by 3 by 3 tensor. Anybody solve Comon's conjecture? Okay, and here's the second open problem. So let me give you a second open problem. Can all the eigenvectors be real? So here we saw that this 13 is quite rare, but it can be attained. But is it true? Can you find for any n and d, can you find a real tensor such that the full complex count is attained by real eigenvectors? So we don't know at this point. The answer is affirmative in the first non-trivial case. So if n is 3, so if we have a 3 by 3 by 3 by 3 tensor, that is to say a ternary form, a curve in the projective plane, then the answer is yes. So our formula for n equals 3 is 1 plus d minus 1 plus d minus 1 squared. So that's 7 or 13. That's this number. And I claim the answer is yes. So let me give you the proof. Right? So every math talk has to have one proof. This is the one proof in this talk. Okay? So I'm going to prove this to you. Okay, so here's the tensor, right? So we have we're looking for a ternary form in the plane. So let me just take n lines in the plane, general lines in the plane. Each is defined by a linear form in 3 variables, x, y, z. I multiply these linear forms. That's my homogeneous polynomial. That's my tensor. So T is a product of D linear forms. Now, what about these lines? Well, there are D choose 2 red vertices. So these are the pairwise intersection points of these lines, and there are D choose 2 of them. And I claim that these vertices are actually, they will be eigenvectors, right? Well, they're the eigenvectors with eigenvalue 0, right? Because there, my product, my polynomial vanishes. These are the singular points. The red dots are the singular points of the blue curve. Singular point means eigenvector with eigenvalue 0, so the red points will be eigenvectors. Okay? Now what happens outside these lines? Well, this line arrangement cuts up the real projective plane into polygons, triangles, quadrangles, and so on, convex polygons. And if you have a convex polygon, or if you have a convex polytope in arbitrary dimensions in a given inequality representation, you have a God-given point right in the middle, called the analytic center. The analytic center is where the interior point method starts. Right? If you have an interior point method to solve a linear programming method, it has to start somewhere. It starts right in the middle at the analytic center, and they are in fact also, if you unravel the definition, they're also eigenvectors. So the analytic centers of the regions are also fixed points. Now, how many regions are there? Let's count the number of regions. Okay, this picture is in the projective plane, so let's do this. 1, 2, 3, 4, 5, 6, 7, 4, 5, 6, 7, 4, 7. Okay, so these 4 lines, 4 blue lines, cut up the real projective plane into 4, 7 polygons. Now that makes 13, and in general, so we found D choose 2 eigenvectors with eigenvalue 0. We found one more real eigenvector, the analytic center, with a distinct non-zero eigenvalue. And now this number plus that number equals the complex count, and that's the end of the proof. Okay? So I've attained the complex upper bound by exhibiting the correct number of real eigenvectors. And we don't know at the moment how to do this in higher dimensions. And if you get bored in the next 18 minutes, you can try to think about the same thing in dimension 3. Let's talk about singular vectors and singular values. Now, so far we talked about symmetric tensors and symmetric matrices. So singular vectors pertain to rectangular non-symmetric matrices. So let's remind ourselves, here's one of the definitions. So suppose T is a rectangular matrix, say with real entries. We're going to be interested in this equation. Tu equals sigma v, where u and v are unknown column vectors of different length. Right? So I have a rectangular matrix, and u and v are column vectors of a different length. And I also want that T transpose times v is sigma u, where sigma is a scalar. Now u and v, these two vectors, are called the left and right singular vector of the rectangular matrix T, and sigma, or rather its square, is the corresponding singular value. So I'm going to refer to this pair of vectors uv as a singular vector pair, and the scalar sigma, or rather the square of sigma, as the corresponding singular value. Let's recast this in terms of fixed points of a gradient map. What are matrices good for? Well, matrices are good for many things. In particular, they represent bilinear forms. Right? So symmetric matrices with the basis represent quadratic forms. Rectangular matrices represent bilinear forms. So my matrix here, if it's an n1 by n2 matrix, represent a bilinear form in two groups of variables, the x's and the y's. Well, let's look at the gradient vector. Let's take the partial derivatives of a bilinear form. Well, that's naturally split up, right? There's the gradient with respect to the x's, and then there's the gradient with respect to t. So every partial derivative with respect to an x variable is a linear form in y, and every partial derivative with respect to y is a linear form in x. Now, it's very natural, thinking about this geometrically, not to define a self-map of projective space, but to define a self-map on a product of two projective spaces. So I have the first projective space of dimension n1 minus 1 has homogeneous coordinates x1, x2 up to xn minus 1. The second projective space has homogeneous coordinates y1 up to yn minus 2. Okay, now let's apply the gradients. This is a linear map now, right? These are linear forms. So let's take a pair, u here and v there, and apply the gradient map. Well, then it maps it to t transpose times v and t times u. Okay, the fixed points of this map are the singular vector pairs. Right? So to be a fixed point of this map means exactly to satisfy these equations. So we have taken the definition of left and right singular vector of singular vector pairs, and we recast them as fixed points of a self-map. But unlike in the eigenvector case, where we had a self-map of a projective space, now we have a self-map of a product of two projective spaces. Now it's pretty clear how to generalize this to tensors, so let's do it. So if we have a general tensor of arbitrary non-symmetric format, n1 by n2 blah 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 by nd, it represents a multilinear form. Right? So by Rubik's cube, represents, if it's a non-symmetric Rubik's Cube, it represents a trilinear form. So now we're going to introduce for the various dimensions. So now I'm looking at a product of projective spaces, a product of D projective spaces, and by definition, a singular vector tuple is a fixed point of the gradient map, thought of as a self-map of the corresponding product of projective spaces. There's a finite number of those singular vector tuples, and the number is counted by the following theorem. This is due to Friedland and Ottaviani from 2014. So again, we have a general tensor of format n1 by n2 by nd. And it's an exact count. So the number of singular vector tuples is given as a coefficient in a generating function. So we're forming a generating function in unknown z1 up to zd. I'm going to look at zi hat, which is the sum of everybody except for the ith. And then I'm going to form the following polynomial. So I'm going to take the product of zi hat to the ni minus zi to the ni divided by the difference. That's a polynomial. And I multiply these polynomials over all I. And then I'm going to take the coefficient of the distinguished monomial. Right? In this expansion, there will be one distinguished monomial that marks the dimensions of the projective spaces, that marks the format of the tensor. So in the Rubik's Cube case, the answer is 37. So if D is 3 and the Ni are all 3, so then this formula says I have a generating function in 3 unknowns, z1, z2, and z3. This expression is simply this one, zi hat squared plus zi hat times zi plus zi squared. You multiply this out. The distinguished monomial that we're interested in is z1 squared, z2 squared, z3 squared, and the coefficient is 37. So we have accomplished answering the two questions on the first slide. If you have a Rubik's Cube, a 3 by 3 by 3 tensor, it will have 7 eigenvectors, and it will have 37 singular vector triples. Let's get to this picture. Let me explain. What's the picture on the cover of the July 16 issue of the Notices? Now, for eigenvectors, we saw, I mentioned, that ODCo tensors exhibit the general behavior. So if you want to understand how many eigenvectors there are, you can focus on ODCo tensors. They will exhibit the general behavior. That is not so for singular vectors. For singular vectors, ODCo tensors are special. And Robeva and Siegel, Elena and Anna Siegel, they asked the question, what can we say about singular vectors of ODCo tensors? In which sense are they special? Well, let's look at this case. Let's look at a tensor of format 3 by 3 by 2 by 2. This defines a quadrilinear form, a multilinear form of order 4, and it has 98 singular vector quadruples. Right? The 98 you get by plugging into this formula. You plug in this formula, so a general such tensor has 98 singular vector. Now what happens in the ODCo case? So in the ODCo case, such a tensor, represented by its corresponding multilinear form, will look like this. Up to a change of basis, an ODCo tensor looks like this. x0, y0, z0, w0 plus the corresponding thing with sum 1. Now these unknowns are homogeneous coordinates and 4 projective spaces. Right? So corresponding to this, now we have a self-map of P2 times P2 times P1 times P1 into itself. P2 is the projective plane with 3 blue homogeneous coordinates x0, x1, x2. The second P2 is green. It has 3 homogeneous coordinates y0, y1, y2. P1, the first P1, is red. It has 2 red homogeneous coordinates, z0 and z1. And lastly, the last P1 is yellow. It has 2 yellow homogeneous coordinates, w0, w1. Well, the gradient map is a very simple monomial map, right? You take the partial derivatives of this. But there are only 18 isolated fixed points. What happens to the other 80? Well, the other 80 come together and they form a two-dimensional variety. They form a surface. And this is a picture of this surface. How is this to be understood? Well, in combinatorics or symplectic geometry, we're going to think about these projective places as simplices, right? So this P2 is a blue triangle, green triangle, red line segment, yellow line segment. The direct product of two triangles and two line segments is a six-dimensional multichromatic polytope. A six-dimensional polytope. And in the boundary of this six-dimensional polytope, we find these subcomplex of two-dimensional faces. And this is the scheme, the variety of singular vectors. So this tells us how the 98 singular vector quadruples degenerate as I move from an arbitrary 3x3x2x2 tensor to an orthogonally decomposable tensor. And it's kind of a very nice visualization for the spectral theory, the singular value decomposition of such tensors. Let's wrap up. I might end a couple minutes early, especially before lunch. Nobody minds if the speaker ends early. So conclusion. Eigenvectors of square matrices are central to linear algebra. Linear algebra runs the world, right? We learned in the previous talk that scientific computing rests on high performance numerical linear algebra. Many things, Google and the rest of it, everybody rests on linear algebra. And the concept of eigenvectors and singular values and so on is central to linear algebra. Now today, many data come in the form of tensors. Many problems are inherently nonlinear, and it's worthwhile to retain this nonlinearity as far as possible, to understand the structure, to retain the nonlinearity as long as possible prior to passing to linear algebra, prior to harnessing the amazing power of numerical linear algebra. Now, eigenvectors of tensors are a very natural generalization. Now, they were really an old concept, but in the context of numerical multilinear algebra, they were pioneered just a decade ago, in particular by Lim and Qi. And now they have many applications. I didn't really talk about the applications, but if you think about any context in which symmetric matrices are useful, maybe covariance matrices in statistics, or Laplacians and mixing times and so on, well, replace the graph by a hypergraph and replace covariance by cumulants, and you get to tensors. Now, this lecture served a second purpose. It served as an invitation to applied algebraic geometry, the use of nonlinear algebra in applications. Now, one thing I would like to stress here is the importance, the very great importance of the word variety. The nicest tensors, rank 1 tensors or rank 1 symmetric tensors, are called the Segre variety and the Veronese variety. Given some data, you really want to get close to these varieties. And that's what we discussed today. Now, why do I say scary? Well, the word manifold is in wide use. The word manifold is a very soothing, comforting word, as in manifold learning, for example. Many people like you have heard the word manifold and it sounds pretty good. Trouble is, most of the spaces of data, many of the spaces of data that you actually encounter are not manifolds, right? If you want to do it like in Bayesian model selection, you want to find the rank of a matrix, then you decide between rank R and rank R minus 1. But rank R minus 1 matrices is the singular locus inside the rank R matrices. So you're naturally forced to encounter, in Bayesian inference, you're naturally forced to encounter, to face the singularities. And some people, I heard this at a conference, it's not so much the curse of dimensionality, it's curse of singularities. So the Bayesian information criterion, the AIC, the BIC, they are just wrong on a variety. But that's not bad, because that's really what the true structure of many problems is. So I like to encourage you to go beyond the comforting, soothing idea of a manifold that looks locally like a linear space and embrace the concept of singularities and to look at varieties. On that note, so it was already mentioned in the introduction, so this is the new journal, the SciEm Journal on Applied Algebra and Geometry. The first issue was published last week. Please visit, take a look at the issue, share the video with your kids and your grandmother. And this is the pictures that you see on the cover page. Let me zip through this. So we talked today in this lecture, we talked about tensors. Here's geometric modeling. There's a spline Bezier surface. This is applied topology, persistent homology, right? There's a topological feature coming from a point cloud. Computer vision, robotics, right? That's a Stuart Go platform. This optimization, this represents semi-definite programming with a nice convex shape in the middle. And this is one of my favorites. This represents coding and cryptography. It's a picture of a quartic, the most singular, irreducible degree 4 surface in three-dimensional space, a so-called Kummer surface. So this Kummer surface has 16 singular points. And abstractly, this is the an abelian surface modulo the involution. So it has 16 two-torsion points. Abelian surfaces, just like elliptic curves, are very important for cryptography. And so this really has a group structure. But that's an entirely different talk, so I stop and thank for your attention.